Okay, we're going to continue our work with problem number 26. This is chapter 20 homework answers. This is part 2. And we're on problem number 26 now. If the 0.1 millimeter diameter tungsten filament in a light bulb is to have a resistance of 0.2 ohms at 20 degrees, how long should it be? Now this, if you look, there's a section where they talk about this, where the resistance is equal to a factor known as the resistivity times the length divided by the cross-sectional area. And if you think about it, it's basically you have a wire, and if you think about it again, use my garden hose thing, basically there are three factors that are important here. Is the medium, which this has to flow through, which is the resistivity, how far it has to go, which is the length, and then the cross-sectional area, which is and those three factors control how much resistance to flow of electrons, in this case, occur. So if we're going to have the area, so we'll take the diameter, which is 0.100 millimeters, which is the same as 1 times 10 to the minus 4 meters, and we'll use the radius, which is half that, so that's 5 times 10 to the minus 5 meters, and the area will be pi r squared, which is pi times 5 times 10 to the minus 5 squared. So the cross-sectional area here is 7.85 times 10 to the minus 9 meters squared. Okay, and there's a table in your book that gives you rho, or the resistivity, and in this case it's 5.6 times 10 to the minus 8 and so we can rearrange this equation such that we solve it for L. L is going to equal RA over rho, and we want a resistance of 0.2, so we have 0.2 times 7.8 times 10 to the minus 9 divided by 5.6 times 10 to the minus 8. And if you do all that calculation, you get 0.0281 meters, or 2.81 centimeters in length. 36. Now 36 talks about the effect of this resistivity by temperature. And the key here is that the new resistance is equal to the resistance essentially at 20 degrees, which is what R0 is, times a factor called 1 plus alpha, which is for each particular material there's a change in resistance, and that's what this alpha constant is, times the change in temperature with 20 degrees being the baseline. So it tells you in this problem, let me read the problem here real quick, that you have two wires, and these two wires, one is copper and one is iron. And the copper has a resistance of 0.5 and the iron has a resistance of 0.525 at the same temperature, 20 degrees. And then it asks the question, at what temperature will their resistances be equal? So what you have to do is you have to say, okay, the copper is 0.500, the iron is, R0 for iron is 0.525, okay? And it wants to know, and this is both at 20 degrees, so it wants to know what temperature is going to equal where those two are equal. So alpha for copper is 3.9 times 10 to the minus 3. And alpha for iron is 5 times 10 to the minus 3. And basically you set these two equal to each other. You say that R0 for iron times 1 plus alpha iron delta T is equal to R0 for copper times 1 plus alpha copper delta T. And if you put these numbers in, so you have 0.525, 1 plus 5 times 10 to the minus 3 delta T is equal to 0.5 times 1 plus 3.9 times 10 to the minus 3 delta T. And these delta T's are the same, okay? And so if you solve for this, you get a delta T of minus 37 degrees. So that means that if you subtract that from 20, the temperature, which both these are the same, is minus 17 degrees centigrade. I assigned problem number 38, but when I read it, I couldn't figure out what they were talking about, and I couldn't find. It says to redo problem exercise 2025, and I honestly couldn't find what they were talking about with exercise 2025, so I basically skipped it. So if you couldn't figure it out either, that's fine. Next is problem number 42. Problem number 42 moves into a new section of power. There's a couple of formulas you need to know for this. P, power, in watts, is equal to I times V. And it's also equal to V squared over R. And so that's important for us to understand that, to do these next few problems. So problem number 42 says a charge of 4 coulombs passes through a pocket calculator in 4 hours. We did this already. What is the power output given the calculator's voltage is 3 volts? Okay, so we know that I, if we go back to where we did this problem before, up here, we know that I is 0.273 milliamps, okay? So let's just write that down. That's equal to 0.273 milliamp, or 2.73 times 10 to the minus 4 amps. And V is 3 volts, so P is going to equal 2.73 times 10 to the minus 4 times 3 volts. And the answer to that is equal to 8.33 times 10 to the minus 4 watts of power. Okay, moving on to number 59. With number 59, we have to do some calculations before we work on the water part. And it goes back to calculating heat output. And so it says, in number 59, it says cold water vaporizers pass a current through water, evaporating it with only a small change in temperature. One such home device is rated at 3.5 amps and utilizes 120 AC with 95% efficiency. What is the vaporization rate in grams per minute? And how much water must you put to vaporize for 8 hours overnight? Okay. And so, first of all, to vaporize a gram of water, if you look it up, the heat of vaporization for 1 gram of water is 2,260 joules, okay? And that's back from that problems we did before. So basically we know that power is equal to IR, or IV, excuse me. So that's going to be 3.5 amps and times 120 volts. And if you multiply those two together, you get 420 watts. Now I'm going to wait and put my efficiency at the end, okay? So let's just work this problem as if, so that's 420 watts is equal to 420 joules per second, okay? That's what a watt is, it's joules per second. So it's asking you, in this problem, it asks you what is the vaporization rate per minute. So you multiply this, so the total amount of energy that you want is 420 joules per second times 60 seconds per minute. And this will tell you the energy you need per minute, that you're putting out per minute. And if you multiply that out, you get 25,200 joules per minute. And since it takes this many joules to vaporize 1 gram of water, if you take 25,200 and divide it by 2260, but then now we'll put our 95% efficiency in there, and that gives you an amount of 10.6 grams of water per minute. Then it says if you do that for 8 hours, so if you're 10.6 grams per minute times 8 hours, and an hour is 60 minutes, so that's 480, or excuse me, let's put it 60 minutes per hour. So that's 480 times 10, and that's going to give you approximately 5,110 grams of water, or 5.11 kilograms of water for an 8-hour evening. 61. What current must be produced by a 12-volt battery operated bottle warmer in order to heat 75 grams of glass, 250 grams of baby formula, and 300 grams of aluminum from 20 to 90? In order to work this problem, you have to start out figuring out how much heat is required to do all that. So heat is equal to MC delta T, right? So 75 grams of glass, and I looked up the specific heat of glass, and it's 0.84 joules per gram degree centigrade, times, and you're changing temperature 70 degrees. So that's the glass. Then the formula is 250, and we're assuming that that's like water, so that's 4.18 joules per gram degree centigrade, plus, and then you have a 300 gram aluminum, and aluminum, if you look it up, is 0.9 joules per gram degree centigrade. And if you multiply all that together and add it up, it takes 96,460 joules of energy to heat that up. Remembering that P is equal to V over I, and this is the P you're going to need. So P, and it says in 5 minutes, so the T here is 5 minutes, or 300 seconds. So P is equal to the work or energy divided by time. And so if you divide these, if you put that in there, it's 96,460 divided by 300. And so the watts you're going to need are 322 watts. And I is equal to P over, P over V. And that's going to be 322 divided by 12. So you need a current of 26.8 amps in order to pull this off. I'm going to stop at this point